The first point I want to make in today's class is to let you know that I follow the book that I've showed on the board here, and the book is the textbook for the course, and it is Continuum Mechanics for Modeling, Simulation, and Design. It is written to support the course, and at the end of every chapter, there are up to 30 or more questions and answers. Those Q&As are answered in full. There is no question that is not answered there. So you might think, okay, what is the challenge for you? The challenge for you is to go to the web and now get those questions again in Q&A, in a CBT form. So if you go there, every time you go there, how much the marks you got for each visit will be recorded. We already know how far you are going. That is going to constitute your continuous assessment. Just go there. But before you go there, make sure you've worked all those questions through. They are at the end of each chapter. Now, you can download this book. If you have difficulty, check on the website and ask the people on ground to show you how to get your own copy. It is absolutely free for download. So it's my book. It's free for you. So there's no hidden costs, no hidden charges. This course this time will not go beyond the first 3 chapters. The first chapter is a review of vectors, which is what we've been doing. Somebody asked me, what are we going to do with this? I am saying you don't understand vectors enough for me to talk to you. You're asking me what you will do with it. What you will do with it is to understand what I'm going to teach next. I'm going to teach you tensors. What do you do with tensors? Because if you know tensors, we can teach you kinematics. And if you know kinematics, we can teach you all the other courses, fluid mechanics, strength of materials, will be taught in a way that connects them to the software you use for design. So you can bring all those knowledge together in designing. That is the whole goal that's the goal of the whole thing. So you have just started the journey. So the first thing for you to do is to understand. If you understand, it will be useful to you. If you don't understand, then what is the point discussing with you what you will do with it? You will do absolutely nothing with it if you don't understand. So that is the first thing I want to make clear. Get yourself a copy, and then the notes, the slides, and all those ones are just expatiations on the things on the materials already covered in the book. I'm following the book as closely as possible. That is number 1. Number 2, you will, like I've explained, the questions in the CBT database are exactly the same questions that I've solved in full, which is now repurposed for the QB and the QBT. So if you can understand the questions and answers, you should be able to do well in the QBT. And if you fail or you have difficulties, sometimes the thing will draw your attention to the pages and the specific things that you are not doing well and what to do to make it better for you next time. We want you to go to the test as many times as possible and improve your grading. So if you go there several times and you get better grades, that will add up to something better for you at the end. There is nothing stopping you from getting full marks. So if you are ready to work hard, but by the time you are getting full marks, you yourself will know that you know everything we have taught you. So nothing comes for free. In this case, there's no magic. So there are solved Q&As in all the chapters of this book. The questions in your database of self-testing are mostly paraphrases from the same Q&A. When you do a self-test, apart from giving you your result, we also supply you with the Q&A or theory that forms the base of the questions missed. This answers the request from some students that we could work out the solutions to these questions. We've already worked them out in the book. This arrangement is better developed here than last time. This is not for you. So make use of this and do your review and correction. But the way you do your review and correction, go back and take the test again. So go back and take the test again if you have any difficulty. That is it. Sometimes the questions in the self-test, sometimes the question may come from the textbook directly. In such a case, you are to read the pages specified in the text to find solutions. So if you miss a problem, I will tell you, go to page 38. What we are saying is that if you go back and read page 38 again, you should be able to answer the question, because the question itself was drawn from page 38. So if the question is coming from a fully solved problem, we will refer to the number of the question. Go and read that through. You should be able to understand. They can help you improve on your mathematical coding. So those of you who are using, I do not insist that you must use Mathematica, but if you have Mathematica installed on your computer, you will find it easier to do this course. And it's a good idea, but I cannot pay for your Mathematica. So if you can pay for it or you can get it any way you like, that's your cup of tea, not mine. So we are starting today the algebra of tensors. So you will have an idea algebraically what a tensor is. Well, what we are trying to show in chapter 2 is to tell you what really is a tensor, for you to be able to answer that question unambiguously, and you know what you are talking about. When you mention the word tensor, what do you mean by it? So it will take you going through the chapter to be able to answer that question completely correctly. So here we are introducing a tensor as a linear transformation. That is a big word. What do we mean by linear? What do we mean by transformation? At the end of today's class, you should be able to understand what we mean by those two terms. What is a linear? When we say, what do we mean when we say something is linear? In contrast to when we say the thing is non-linear. You should be able to know when something is linear and when something is non-linear. Just to whet your appetite, if you look at yourself in a plain mirror, you are going to see a linear image. If you look at yourself in a convex or a concave mirror, you are going to see a non-linear image. You can see that the non-linear image is sort of, you might think it is distorted. It is not distorted, it's the same image, but it is giving you the image non-linearly. That is an idea of what the difference between a linear transformation and a non-linear transformation can be seen as the difference between what you have in a plane mirror as compared to a non-plane mirror. If the mirror is not plane, the transformation it gives the same image you are supplying, but the results are different. So it's a transformation quite all right, but one is linear, the other one is non-linear. Now, it's a transformation because the image you get is a result of the image you supply. So if you supply another image, it will give you another transformation. If you supply a tall person, to give you, if it's linear, it will give you a tall person. If you supply a short person, if it's linear, it will give you a short output. Those outputs are the transformations of the original. So you distinguish between the initial object, the input, and the output. The output is what we call the transformation, and the other one is just the input of the transformation. So there is nothing so difficult about linearity and transformation, but you must get that idea very clearly. By the time you understand linearity and transformation, you're already 80% on your way to knowing what a tensor is. So a tensor is a linear transformation. Now, objectives of today's lecture. We will introduce a transformation as a rule, a process or procedure for obtaining an output when an input is supplied. That concept of linearity, that the concept of linearity of a transformation is fully established. So we will show you what a transformation is. The transformation is the rule. Then after you have fully understood the rule, we will now have to show that that rule itself is linear. To know that a tensor, number two, to know that a tensor must firstly transform a vector to a vector, and secondly perform the transformation linearly. That is, if you want to know whether something is a tensor or not, supply it a vector and see what it does to it. If it transforms it and gives you another vector, then you are halfway to knowing that it is a tensor. The next thing you check is that transformation linear? Even if it transforms a vector and gives the output of another vector, if the transformation is not linear, it is still not a tensor. If the transformation is linear and it does not give you a vector when you supply a vector, those two conditions must be satisfied for your transformation to be a tensor transformation. A tensor is something that transforms the input of a vector to the output of another vector. The vector you supply is not necessarily what you get. It is related, but it's not necessarily the same. It can be the same, but it's not necessarily so. But whatever, you must get a vector. If you supply a vector, you must get a vector. And that transformation must be linear. So you need to understand what we mean by a transformation is linear. We are going to fully define what we mean by linear transformation. Number 3, to be able to recognize a tensor transformation and a non-tensor transformation. So I can give you 2 transformations and I can ask you, what did the transformation? Is it a tensor? Is it not a tensor? You should be able to answer yes or no by just checking. When I supplied a vector, did I get a vector back? When I got a vector back, was it a linear transformation? Then what I have is a tensor. If any of the rules got broken, then what I have is not a tensor. Number 4, to learn to work these things out, knowing they cannot be known just by looking at them. Some of you can be lazy. You want a formula that just look at the thing, you have the answer. It's not going to work out that way. You will need to sit down and sweat it out before you can know. So anything that is good comes with some effort. So there will be some, you need to have put in some effort to be able to get the correct answers here. But we shall show you the steps to take to get the correct answer. I want to omit pages. I want to omit the next 2 pages because they are not really what I want to talk about now. So let us go straight to defining the tense. What I'm going to do here, I want to show you that the sun, the sun, for those of you who speak Yoruba, I wish I knew it in Igbo or other languages that you speak. I want to show you that we can say that the shadow given by the sun is a tensor transformation, in which case the sun itself is a tensor. Let us see why that can be true. Because, for instance, you can take a vector as something that has magnitude and direction, which can be represented by a directed arrowed line. If we take it from that point of view, then if I point some of those arrows in the same direction and put it in the afternoon sun, it will cast a shadow. So we can say the shadow is the transformation, and the input is the arrowed line. And we want to say, okay, you can see that if I give an arrowed line, the shadow gives me back another arrowed line, which is not necessarily the same as the original one. Now, we will now see what we would need to show to make sure that transformation, to see whether that transformation is linear or not. So let us clarify popular usage. What is a tensor? Is the sun a tensor? Clarify popular usage. The word tensor, by a historical accident, does not mean tensor. Whenever you hear that word with no adjective, you are talking about a second order tensor. So if somebody just says this is a tensor, he's really not talking about a tensor in general, he's talking about a second order tensor. But because there are tensors of all orders, the way we resolve the problem is this. Anytime we are not talking about a second order tensor, we will fully define the tensor. If it's zeroth order, we say zeroth order. If it's first order, we say it's first order. If it's third order, we say it's third order. If it is fourth order, we say it's fourth order. In this course, you are not going to see any tensor higher than fourth order. So they exist. There are sixth order tensors, there are higher order tensors that have practical uses. But for this course, you will likely only see second order tensors, and occasionally you will see some third and fourth order tensors, and you can count them. It cannot be more than 2 or 3 that are useful that you will see. You've already seen one. It's just that you didn't know it is a tensor. We didn't reveal the full. And let me just let the cat out of the bag. That alternating Levi-Civita symbol that had 3 indices is actually a third order tensor. But we didn't, because you have not been taught tensors, we couldn't tell you the full gist at first. But after we finish the algebra, you will see that that's actually a tensor. So when used without any adjective, you are talking about a second order tensor. If you mean any other tensor, you must be specific. Consequently, when we talk about a zero order tensor, it is a scalar we are talking about. A zero order tensor is a scalar. A first order tensor is a vector. Assumption. We are assuming you are familiar with scalars and vectors. We shall be defining second order tensor in the following slides. There are higher order tensors that will be introduced later. That assumption, I didn't make the assumption completely. That's why I devoted the whole of the first chapter teaching you about vectors, assuming you know about scalars. I was not satisfied that your knowledge of vectors was good enough. So that's why I had to create a whole chapter and just clear that backlog of bad teaching or bad knowledge of the knowledge. I am hoping that members of this class think now that they know much more about vectors than they knew before. If you did, then we are successful and we have prepared you to take a course on the algebra of tensors, which we are starting right now. If we are not, then too bad. Now, is the sun a tensor? If we give the sun a vector, can it make another vector in response? Of course, yes, by creating a shadow. And that shadow is a vector because it has magnitude and direction. So until you are supplied with the rule, the tensor is not defined. So if we have a rule, we supply something to the sun, we let it cast a shadow on it, and we are saying that the output is the shadow and the input is what we supplied, like I've showed. Then that is the rule. With that rule, the sun itself is a tensor because give it any directed line, it will give you a shadow of it. And there is some, the next question is it linear? We would look at that. So mathematically, mathematicians and those of us who use mathematics, we like to write things in very strict, small form. We are going to write it in a way, and I don't want you to get lost in the way we write it. The way we write it is just is for notational convenience. What we are doing is what I've already explained. There is notational convenience. Don't get disturbed by the notational convenience. A tensor is a linear transformation of a vector that produces another vector. Mathematically, we can say if U, V are members of the Euclidean vector space, don't take it as if it is just the E there is a set of vectors. That is, if U and V belong to the set, then the transformation T, which belongs to the linear transformations, with the operand U and output V, we can say V is equal to TU, where T is the tensor operating on U to supply us the answer V. We can say the transformation of U through T is V. Now, there is a side note here. Writing it as V is equal to TU is a matter of convenience or convention, s'il play, whichever one you choose, whether it is convenience or convention, we just choose to write it that way. There is nothing sacrosanct about the way it is written. What matters is not how you write it, but what you mean by what you have written. It could have been written as V is equal to T with bracket U. Sometimes V is equal to T with bracket U can mean T times U. It can mean T is a function of U, or it can mean that V is the transformation of U. And some other textbooks, they will write it as V is equal to T dot U. We will not do that in this class for a reason. Anytime we use dot, a single dot, the things on both sides must be both vectors so that it is a dot product that produces a scalar. So we are not going to use that. We are not going to use this method. We're not going to write it like this. We're also not going to write it in the functional form. We prefer this concatenation form where you will write T followed by U on the right-hand side. We will write the tensor on the left. We write the vector it is transforming on its right. But like I said, that is just our way of writing it. So if we are given T and it gives us V, which is TU, it will be a tensor if that transformation is linear. It is a transformation from one vector space to another. That is, you can say it's transformation from one vector set to another. If you do not understand what a vector space is, just say vector set. A set, just a collection of vectors, that's all. Depicting the set of all tensors as L, we can also write that as saying that L is such that it transforms from E to E. That is, the object it transforms is a vector, which is a member of E, and the object it gives you at the end of the transformation is also another vector, which is a member of E. So it is transforming the set E to E, and it is a linear transformation. What you have on this page is a mathematician's definition, but do not worry about it at all. Don't worry about it at all, because the question you ask yourself, what do we mean by that? What we mean is that we will give you a vector and we will give you a rule that will use it to produce another vector. That rule would be a tensor if the transformation you have done is linear. If the transformation you have done is not linear, then it's not a tensor. That's all. That's all that the mathematician is saying on this page 10. So do not worry about anything there. There is nothing there except just a way to write it down, just a way to depict it, the way to say what we have just, all that we have been saying. You know, a mathematician will take all the words you said in 30 minutes and he will write it in a page in a very convenient form for easy remembrance. That's all there is to it. There's nothing more than that. So if you have any difficulty with it, ask questions, but there is nothing to it more than what I've just explained. Okay, so let us go back to the sun example. And now let us see what we mean by linear transformation. In the figure here, let the brown, which we depicted at X, the second one, if you are coming from the right, let it also assume that's lying on the ground. So it coincides with its own shadow. So that one coincides with its own shadow, but the others are lying at an angle. Because they are lying at an angle, they do not coincide with their shadows. So you can see them and you can see their shadows. So in the figure here, let the brown arrow labeled X represent the vector line on the ground. Here, we are going to just take the simplistic definition of vectors that we learned from secondary school, that is something that has magnitude and direction, which can be represented by an arrow drawn in a particular direction with a magnitude depicted by the length of that arrow. So that is how we are interpreting a vector for now. There are better ways, there are much more rigorous ways to define a vector, but I do not want to. That's what I'm supposed to teach today, but I can see that, yeah, we don't need that. We can just go on without that. Okay, so assume that the other arrows are vectors casting familiar shadows on the ground. This is something you are used to. Examine what we are doing now. We want to know whether this transformation is linear or not. And what we would do is examine the relationship between the arrows and their shadows. We use the word transformation in describing the relationship. So by transformation, we are talking about the relationship between the vector and its shadow in this case. So the transformed vector is its shadow, and the input is a vector. And the tensor is whatever is responsible for making that transformation occur, which in this case is the sun. So if we can prove that the transformation given by the sun is linear, then we can say that even the sun itself is a tensor. That's it. There is nothing, anything that you can see a particular way, if that it can change something from one vector, you can change one vector to another, and it does so linearly, then it is a tensor. We already can see what it means to transform from one vector to another. What we are yet to talk about or to understand now is what is the linearity? Why is it? How do we know whether the transformation is linear, and how do we know the transformation is not linear? But that you put an input of a vector and you get an output of a vector. It's clear here. The input is the vector and the output is its shadow. And if by vector we mean a directed line with an arrow, you can see that in each case we get the same thing. So that is clear. So when you want to know whether something is linear, there are questions you ask. What determines the size or the magnitude of each shadow? If two vectors are equal and they are given to the sun at the same way, what can you say about their shadows? For instance, you can see that the blue vector here and the blue vector here, they are the same. Are their shadows the same? So if their shadows are the same, that's important. If there are two vectors that are pointing in opposite directions, will their shadows also point in opposite directions? If one vector is twice another, will its shadow be twice the other? So if I have one vector and it's twice as big as another one, will the shadow be twice as big? If we add two vectors, what is the relationship between the resultant shadow? Will the addition of the two vectors give the same thing as the addition of their shadows? So the shadow of the addition, is it the same thing as the shadow of the individual vectors added together? And the vectors, if we add two vectors, what is the relation between their resultant shadow, the individual shadows, and the vectors that made up the shadow? For instance, coordinate transformation. We talked about that last time, and we say it's a dyad. If the figure depicts a coordinate transformation, if a vector v was fixed to the original orthonormal coordinate in such a way that it moved with it, what will its component be in the new system? What will the components be in the old system? How will the result of several vectors transform? What about a weighted sum? Will a weighted sum of vectors transform as a weighted sum of shadows? What is the relationship between the image of a weighted sum of vectors and the image of the weighted sum? What is the relationship between the image of the weighted sum of vectors and the image of the weighted sum and the weights as a result of the transformation? The dyad. We encountered the dyad product of two vectors in the last chapter. Recall that the dyad is defined by the way it transforms vectors. For the dyad, we had a specific rule. If you use the dyad to transform a vector, the answer you will get is the vectors dot product with the second part of the dyad multiplied, which would now a scalar quantity, multiplied by the first vector. That is the rule. That is the rule for the dyad. The question we're asking now, does that rule always produce vectors? Of course, yes, it always produces vectors when you supply a vector. The next question is it linear? We know that the result of that transformation is another vector, satisfy the first requirement to be a tensor. Is the dyad a tensor? We will reach that conclusion by the answers provided by the questions we have been raising. If the dyad operates on the sum of two vectors, the weighted sum of several vectors, the scalar multiple of two vectors, etc., what is the relationship between the transformed vectors, the originals, and the weights? It is that will tell us whether the dyad is a tensor. It has passed the first test, but has it passed the second test? Let us take the simplest tensor you can imagine, and it is called the identity transformation. We are going to take the identity transformation through our tests and try to come up with answers. Identity transformation. We represent the identity transformation by the symbol I. Its characteristic may, at first look, appear trivial. Please Don't think that the identity transformation is trivial. It is not trivial at all. It does absolutely nothing to the vector it transforms. So mathematically, if I give you u, if you use I to transform it, the answer is u. If I give you v and you use I to transform it, the answer is v. It is called the identity transformation. It does nothing. So what happens if I transform u plus v? Of course, the answer is u plus v. But suppose I transform u separately and I transform v separately and add the result. Is the result the same thing as the result I get when I transform them together and as when I transform them individually? If the result, if that first question is true, then the identity transformation is linear and therefore is a tensor transformation. If I transform alpha u plus beta v and I get alpha iu and beta iv, if this is true, then it is an identity, it is a linear transformation. Therefore, the identity transformation is actually a tensor. The questions. Number one, is the identity transformation of a sum equal to the sum of the identity transformations? The answer here very easily is yes. Is the identity transformation of a scalar multiple equal to the scalar multiple of an identity transformation? Again, the answer is yes. Is the identity transformation of a weighted sum equal to the weighted sum of identity transformations? The answer again is yes. Because of that, we can say the identity is a proper tensor transformation. So the identity is a tensor. Remember, how do you define the identity? The identity is something that does absolutely nothing to the vector you supply it. It does nothing. Doesn't do anything. It gives you whatever you give it, it gives it back to you. That's called the identity. The identity may look useless, but it is so fundamental. For instance, the number 1 is so neutral. You multiply anything by 1, you get 1. But that 1, innocent as it looks, is the basis of a lot of other things. When you mix it with other things, you will see what happens. We have seen 3 tensors already. The first one is the dyad. The second one is the identity. And the third one is the annihilator. The annihilator tensor gives you the 0 vector for any vector you supply. It bumps it. It turns it to 0. So it is customary to represent the annihilator tensor by one big O. One big O. Its characteristic may at first appear also trivial. It turns every vector it transforms to the 0 vector mathematically. If you transform U by O, you get the 0 vector. That's how you define the annihilator. So we again put our questions to the annihilator. So if you add 2 vectors before you transform, and you transform them individually, are you going to get the same answer? If you have a weighted sum, will you get the same answer? And if all those answers are correct, you will see that the annihilator is also a tensor. So we have already seen 3 tensors: the dyad, the identity, and the annihilator. The next tensor we will be interested in is called the spherical transformation. What's a spherical transformation? The identity transformation and a given scalar, that is gamma, is a function, is a member of the real space. The real space is the set of real numbers. So if we represent the spherical tensor S as gamma I, so it's a product, it's multiplication of I by a scalar. So the question is, we are going to pose our familiar questions, 3 questions. Let us go back to the questions so that we don't forget. The questions are on page 16. Is the spherical tensor of its transformation of a sum equal to the sum of the spherical tensor transformations? Is the spherical tensor transformation of a scalar multiple equal to the scalar multiple of the spherical tensor transformation? And so on. If the answer to those three questions is yes, then we can now say, what answers do we have to our familiar questions when we ask them about the spherical transformation? If the answer to all the questions asked above is, in each case, the transformation of a sum is the sum of the individual transformations. The transformation of a scalar multiple is the scalar multiple of the transformation of the initial vector. The transformation of a weighted sum is the weighted sum of the transformation of the constituent vectors with the same weights. Then we can conclude that we have been dealing with tensors. The transformation we have discussed are all linear transformations, and because they are all linear transformations of vector into vector, then they are tensor transformations. So number 4 is the spherical tensor. So number 0 is the sum. Number 0 is the sum. Number 1 is the dyad. Number 2 is the identity. Number 3 is the annihilator. Number 4 is the spherical. All of these things are linear transformations. Simple tensors. The shadow or the projection. The coordinate transformation, the dyad, the identity, the annihilator, the spherical, and the vector cross, as defined, are all tensors. They transform vector to vector linearly. The identity and the annihilator are essentially the same. It's only the gamma that is different. For the annihilator, the gamma is 0. For the identity, the gamma is 1. So the spherical tensor covers both the annihilator and the identity. So if we can prove a result for the spherical tensor, we've already proved it, not just for the spherical tensor, but for identity tensor, annihilator tensor, and the spherical transformation. So let us look at the spherical transformation. Given U and V are vectors, and alpha, beta, and gamma are real, and the identity tensor is I. We want to test the transformation S is equal to gamma I U for linearity. So for linearity, we first of all, we have how many equality signs here? We have 5. As we are moving from one equality to the other, you can take a note and write the reason why that is possible. First of all, if we want to transform alpha U plus beta V by S, it is equal to gamma I, because S itself is gamma I. That is the definition of S. Transforming alpha U plus beta V. So I want you to tell me, I will go back to the chat room. I want you to tell me why the second equality sign is correct. I go to the chat room and tell me, because there are 1, 2, 3, 4, 5. The first equality is just rewriting gamma I for S, because that's the definition of S. The second equality here says this is equal to this. I want somebody to go to the chat. I want you to go to the chat room and tell me why the second equality is correct. So I will go and meet you in the chat room now. Why is the second equality correct? Okay. Okay. So, okay. I've seen the answer from Flourish, from Patrick, from Monique Consola, from Fagbemi. Okay. So by the definition of the identity, so you agree with me that the first and the second equality is correct. Good. So let us move on. Let us move on then. Let's move on. So why is the third equality correct? Why is the third equality correct? The third equality, why is it correct? Why is the third equality correct? Flourish, you almost got it, but you are wrong. It is not the commutativity. It's not the commutativity that is it's the distributive law. That is good, Patrick. It is the fact that multiplication it distributes over addition. So it is Patrick, then Caleb. Caleb, you are right. And what further answers? Please try. Look at it and tell me. One more answer, I will move on. Don't waste time. Somebody else should talk. Yes, I can see your correction, Flourish. Yes. One person more before I move on. Why is the third equality correct? It is distributed. Must that opening the bracket? Great, Patrick. Good. So we move now. We move on. I'm sure you know so the question I'm going to ask you now is why is the fourth equation correct? The fourth equation, why is it correct? Again, because we can put the identity tensor anywhere. Since it does nothing, putting it there doesn't mean anything, doesn't change anything. So now, lastly, why is the last equality correct? Why is the last equality correct? Why is the last equality correct? Chat room again. The last equality, the fifth equality, why is it correct? Yes, Patrick, you are correct. Yes, Fagbemi. You can see because the definition of S. No, Omotola, you are wrong. S is not equal to I. S is gamma I. S is gamma I. Yes, substitution, Patrick. Yes, Olamilekon, you are right. Okay, so you can see how we have gone step by step. Because if you now compare the last equation to the first, you can see that the spherical tensor applying to a weighted sum is the same as the weighted sum of the results. You can see on the right-hand side, you have the weighted sum of the results. On the left-hand side, you have the transformation of the weighted sum. The transformation of the weighted sum is the weighted sum of the results, showing that the spherical transformation is linear. So we have proved in these 5 lines that the spherical tensor is a linear tensor. Sorry, it's a linear transformation. And if it's a linear transformation, and when you give it a vector, it gives you another vector, we have carried 3 proofs in one move. We have proved that the identity tensor is linear, the identity transformation is linear, the annihilator transformation is linear, and the spherical transformation is linear. We have proved that all those transformations are linear, and therefore they constitute tensor transformations. So we can see. So we have started carrying. We have now done it for identity, for annihilator, and for spherical. We have done it for those 3 already. So the linearity of the annihilator as well as that of the identity are already contained in that of the spherical, since they are special cases of the latter. Their proofs are included here only for instruction purposes, as their linearity can be established directly as follows. I don't want to go into that again because I've already carried that. So let us now go to the dyad. We are now on page 26. We'll do that before we go on break. Given A, B, V that are vectors, when I want to say 3 things are vectors, that is how a mathematician will write it. And I find us adopting that because it's easy. The dyad A dyad B, A dyad B is defined by the transformation A dyad B operating on V is equal to A times the scalar B dot V. That is the definition of the dyad. So that the operand input V is a vector and the output A times a scalar is also a vector directed along the first vector of the dyad. The tensor credentials of this can be found. The tensor credential of this can be found if we find that the dyad transforms the linear combination. If we find how it transforms the linear combination, we observe that the weighted sum alpha, if u and v are vectors, alpha u plus beta v is also a vector. Where I want you to go to the chat room and tell me why, if u and v are vectors and alpha and beta are scalars, why can we conclude that alpha u plus beta v is a vector? I want you to tell me, because you might know it is, but you may not be able to explain why it is. Can you explain to somebody to an unbeliever, somebody who is doubting, that this thing is actually a vector? If u and v are vectors, alpha and beta are scalars, alpha u plus beta v is a vector. Go to the chat room and tell me why it is so. Well, I'm not agreeing with you, Patrick or Lasubomi. Patrick, your second answer is getting closer, but it hasn't. By the last equation, we can say that S also abide. No, it's just a linear combination. Aishat, you are close. You are close, but I'm not satisfied yet. You will not convince an unbeliever that way. Alpha, now Khalid is talking. Alpha and beta, we just scale the vectors. So it scale the vectors, and then so you are just adding two vectors, and the sum of two vectors will always give you a vector. You see, the alpha and beta scale the vectors into other vectors, and the plus between them does the addition. So when alpha and beta scales the vectors, then the addition of two vectors will give us a vector. We know that. If you add two vectors, Patrick, we're not talking about a dyad here. We're just talking about if alpha and beta are scalars. Is that exactly what you said? Well, you probably meant it, but it wasn't explicit. I know, I feel you know what you are saying, but I wanted it to be explicit. That's all. The multiplication of a scalar and vector is still a vector, and then you can add the two together. Okay, good. So I am happy that you are awake. So the question is, does the dyad transform this sum to a vector? How does the output vector relate to the input? Okay, so let us start. We are now on page 27. We now want to apply a dyad to the weighted sum. So we are going to go line by line. Why is the first equality correct? Chat room, why is the first equality correct? The first equality, why is it correct? On page 27. Why is the first equality on page 27 correct? I'm still waiting. Why is the first equality on page 27 correct? Yes, we have already said that the weighted sum is a vector. So what we have done is we just applied the dyad operation. That's it. So that first I will bring it up. That first expression is taking the fact that we could have said alpha u plus beta v is w. If we wrote it as w, we will see that this is correct. So because it would have been a multiplied by b dot w, where w is just this weighted sum, because the weighted sum is a vector. So The next thing now, why is the second equality correct? Why is the second equality correct? Yes, Patrick, you are right, but please state it more clearly. It is a distributive property. The dot product is a product, so it's distributive over addition. The dot product is a product. Because it is a product, it distributes over addition. So that is that. Okay, so we move on. Why now is the third expression correct? Well, Patrick, I don't think you are right here. What happens is that if you look at the second line, the two things that are being added on the second line are scalars. The two things that are being added are scalars. So product must distribute over them because they are dot products. Inside the bracket, you have two dot products. So that means that each one gives us a scalar. So if you represent that scalar as t plus s, so a product must distribute over them. So it is not just the, so all we did, yes, so that's it. So Jola, you can see, Jola is getting it right. So the others, you see, I am wanting you to state the things you think you know. Sometimes it is important to be able to state them mathematically, because you will just say, yes, it's obvious. Why is it obvious? It's obvious to you. How do you tell somebody for whom it is not obvious? There must be a reason. So you can see that by the time you get to the last line, all we've just did is to rewrite it by our understanding of the, we're just reversing the definition of the dyad. That's what we are doing, because you know that A dyad BU is written as A times B dot U, and A dyad BV is written as A times B dot V. So if you now compare the very last thing to what we started with, you can see that the dyad operating on a weighted sum is the same thing as the weighted sum of the dyad operating on the individual with the same weights. With that, we have established the linear credentials of a dyad transformation. The linearity credential of a dyad transformation has been established by showing what happens when it is operating on a weighted sum, showing that the dyad is a linear transformation of a vector to a vector and therefore a tensor. We will take a 10 minutes break. Okay, I hope you are all back. So let us move on. We want to go to the next transformation. There's a transformation we defined on this page. We introduced the shadow transformation here as if there were parallel rays of light creating the transformation. When this happens, it's called a projection. The transformation is called a projection. In order to establish tensor credentials, we shall regenerate this situation mathematically. Introduce the same projection transformation. So what we were doing with the sun just now, we are doing it now mathematically. The transformation of the sun we showed graphically the other time can be mathematically written as 1 over the square of the magnitude of x with x dyading itself. You will agree with me that when x dyads itself, if you operate this on any vector, the result will always be pointing in the direction or the same direction as x. The second thing you might notice, if you are careful, is that the magnitude of the vector v will never change. It will be the same as the magnitude of the result. So those are the two things that will happen. The input as well as the output will have the same magnitude, and the output will be directed in the direction of x. We don't need to prove anything here, really. If you look at the fact that this transformation itself is simply a scalar multiplied by a dyad. We've already proved that a dyad is a tensor. Therefore, if a dyad is a tensor, the projection defined by this dyad is also a tensor. But if you want, you can go through the motions, and we are going to get the same thing that we did before. So we can get the same thing in these steps. But we really don't need that proof, because we've already proved that the dyad is a tensor. Therefore, multiplying it by a scalar remains a tensor. So let us now look at the coordinate transformation. Let's look at the coordinate transformation. Given a set of coordinates with basis vectors E1, E2, and E3, we can transform to the coordinates basis xi1, xi2, xi3 with the transformation xi I dyad EI. You must not forget that this is a sum of three. This is like xi1 dyad E1 plus xi2 dyad E2 plus xi3 dyad E3. That is what this is, because the repetition of I in this product means that there is a summation implicit in it. It is very easy to prove that this is a linear thing. If you transform any vector v referred to E1 and suppose v is 2e1, 3e2 minus e3. If you transform it, what you are going to get is 2 xi1 plus 3 xi2 minus xi3. If one system is a rotation from one, then the other transformation is also a rotation. So you can see that this one, if you double the vector, it will double the result. If you transform two vectors, it will be the same thing. So the coordinate transformation is easily shown to be a linear transformation, and we do that here. The same thing we have been doing from page to page. If you go through this slowly, you should be able to explain the meaning of each equality sign at each top. Each equality sign, there's nothing trivial about the equality signs. And then the final result is the first thing compared to the last thing gives you the final result. That is, if you do a coordinate transformation on alpha u plus beta v, it's saying as if you did the coordinate transformation on each of them and then use the same weights on them afterwards, meaning that the transformation is also linear, satisfying the second condition to be a tensor. Now, we are going to introduce something that can be confusing if you are not careful. There is a tensor called the vector cross. There's a tensor called the vector cross. And that vector cross is actually no longer a vector, but a tensor. We introduce additional transformation here. We show to be a tensor. It is called the vector cross. You have been able to create a tensor from two vectors. We define the vectors cross here as a tensor created from a single vector using the well-known Levi-Civita symbol. Given a vector v is equal to v1 e1 plus v2 e2 plus v3 e3, we define the vector cross as simply minus eijk vk ei circle times ej. So the vector cross is also defined as a dyad. It's a dyad of ei and ej. So that is the vector cross. You remember, if we look carefully here, that there are, in this case, there are 27 components in this expression here, because there are 3 dummy variables. So there are 27 components, and out of those 27 components, because eijk is involved, please go to the chat room and tell me how many of them will be non-trivial, how many of them will be non-zero out of these 27. I want to be sure you remember how many of them will be non-zero. How many? Okay, so you remember only 6 of them will be non-zero. and it is very close to our vector product of our but what we are doing here is that we can define something in tensors that make the vector product of vectors completely irrelevant. So because when you now have the vector cross operating on that vector, is going to give you the same result as if you are taking the vector product of that vector in the vector cross and the vector of interest. So how do we prove that this is a tensor? There's nothing really to do to prove that it's a tensor, for the simple fact that EIJKVK is a scalar. EIJKVK is a scalar, and what you have left inside this place is a dyad. So since what is left is a dyad multiplied by a scalar will always give you a dyad. And so you are just multiplying by a scalar, even if there are 6 of them, each one of them is a dyad. And if we have already proved that a dyad is a tensor, so this must be a tensor. How do we prove that this is a tensor? Prove that it transforms vectors to vectors and that the transformation is linear. The first task is straightforward because what we have here is a scalar multiple of a dyad. So it transforms a vector to vector. And we can write it out here, and we can see that if we do it, we can see that a vector cross defined by the equation we defined before is still also a tensor transformation. So a tensor, we have looked at several examples now. We have got up to 7 examples. And we say a tensor is a linear transformation of a vector that produces another vector. Mathematically, we write that given u and v are vectors, then the transformation T is a linear transformation. V is equal to Tu is a tensor if it is linear. It's a transformation from one Euclidean vector space to another. Depicting the set of tensors as L, we can write T belonging to L, where L is such that it transforms a vector space to another vector space, and it's a linear transformation. That's the definition there again. So we can write it like a black box. That is, what do we mean by a linear operator? That is, if there's a T which is a linear operator, if you supply a weighted sum, the answer you will get is the weighted sum as if you supply them one by one, with the same weights. So if the operation is linear, this page 35 is what defines a linear operation, because you must show that your operation is linear. If I can show that the operation is not linear, then it's not a tensor transformation, even if it transforms a vector to a vector. Vector to vector transformations are, every transformation we have seen so far has been shown to be a tensor. This begs the question, are all vector to vector transformations tensors? The answer is capital no. They are not necessarily tensors. Recall, in order for the transformation to be a tensor, in addition to having operand and output as vectors, it must also be linear. Examples of vector to vector operations that are not tensors are easily found. Here are some. TV, which is equal to E1 divided by the magnitude of V. If you want a proof of this, go to question 2.2 in the book. And then this other one, the second one, is question 2.3. The proofs that these are not tensor transformations are in the references you are given. I think I still went to do it here, despite the fact that I turned it. But I'm not going to waste time on that. I'm not wasting time on that. So this shows that the vector cross is a tensor transformation, and there we want to see whether the inverse of a tensor is also a tensor. Well, I think basically I've finished what I have for you today, and the other things in the note are not for your set. So I've already I will edit those out so that you have only what is yours. So let us go back to the beginning and see what we said we are going to try to achieve today, and see whether we achieve them. If we have achieved them, then there's no need to detain you any further, because you have had a busy day. So Important to note. Objective of today's lecture. A transformation is a rule, a process or procedure for obtaining an output when an input is supplied. That the concept of the linearity of a transformation is fully established. I hope we succeeded in doing that. 2, to know that a tensor must firstly transform a vector to a vector and secondly perform the transformation linearly. We've explained what it meant by linearity of transformation. Number 3, to be able to recognize a tensor transformation and a non-tensor transformation. It's either that the thing doesn't transform vector to vector or it doesn't transform it linearly. Anytime it violates any of those two, it's a non-tensor. To learn to work these things out, we've worked several out. You can see that it is a systematic working out. It's not something that just becomes obvious. So not just by looking at them. So objective of today's lecture has been achieved. I will wait for 2 minutes. If there are questions, I will answer them. If not, the admin can stop the class. So I'm going to go to the chat room and I'll wait there for 2 minutes. If there are questions on today's lecture, I will answer them. Or at least, if I can answer, I will answer them if I can. If I can't answer them, I will tell you. So any questions? Okay, Onyekonsola, go ahead. Ask your question, Onyeko. Well, I don't have the book before me. I will take a look and I will try and send you an answer. I don't have the book before me right now. Oh, are you talking of page 22 of this slide? On the slide. Oh, okay, good. Let me go to slide page 22. I didn't know you were talking about the slide. 22. Okay, so I'm on slide 22. What did Onyekonsola say is the problem? You don't understand equation 3 and 4. You don't understand why it is 3 and 4. Okay, 3 and 4. Let us see. The equality 1, 2, 3. Yes, the equality 3 is distribution. If you have gamma multiplied by a sum, it is you can multiply it individually. That's it. You can multiply individually. And the fourth one, since I does nothing, so U and IU are exactly the same. V and IV are also exactly the same, since I does nothing. So whether you write V or you write IV, it's the same thing, since I does nothing to it. It's just like if you have X and I say 1X, or if you have Y, I say 1Y. Y, 1Y and Y are the same thing. So that is 3 and 4. The third one is coming from the second one, is that gamma is distributive over addition. There is a distributive property of multiplication over addition. That is what happens to equation 3. And equation 4 is that U and IU are exactly the same because of the definition of I. By the definition of I as the identity transformation. So let me see whether I've whether Onyeko understands that. Onyeko, you are not answering. Is it clear? The second time, how did beta turn to alpha? Did beta turn to alpha? Let me see. Is there an error there? Let's see. Did the beta turn to alpha? Oh. There's an error. Thank you, Unicom, for drawing attention to that. So I can correct it straight away. Beta cannot turn to alpha. No. Okay, Oyiko, thanks for drawing attention to the error. So I've corrected it, as you can see. Let's see. I think it's corrected now. So you cannot just turn to alpha. So, any other question from the class? Any other question? Well, I can tell the admin, please, you can close the class now. No questions. Goodbye till next week.